University of Roorkee, followed by a master's from Wayne State University. Then he went on to get a doctorate from University of Minnesota. And parallel and distributed computer architectures are his favorite research areas. And I welcome you, sir.
Thank you very much. It's a pleasure to be here. I come here quite often. I have distinguished colleagues I have a great deal of respect for. Murli, thank you for setting this up. So I like to keep these things informal. Stop me anytime, ask me questions. I'll try to keep it to within an hour, but if you ask me lots of questions, it's your problem. But nevertheless, do ask me questions. I'd rather you talk than I talk. I'm going to talk about something that you probably are all fairly familiar with. Once again, if you're not, ask me questions. This has to do with how you use large-scale distributed systems. And I'm sure many of you have heard of something called MapReduce. Many of you might have programmed MapReduce. And what I will talk about is how things may potentially go wrong in MapReduce, how you get them right, and how some really trivial questions that we thought we knew answers to are really questions we do not know answers to at all. Okay? So, once again, my name is Ananth. I'm from Purdue, and what I'm going to talk about is work of a number of other people. George was my postdoc, who's now at IBM Research. Naresh is still my student. Karthik is my student, who's now at Cloudera. Adnan is my student, who's now at Google. So it's a lot of people who worked on this, and I only take the credit. I don't do the work. All right. So let's start with what people use things like MapReduce for. Okay. So you probably all heard of things like PageRank. I'll also talk about something interesting which we do a lot of in our lab, which has to do with taking really large graphs and lining up graphs in such a way as to find out large overlaps in these graphs. I'm going to distill all of these down to something very simple, multiplying a matrix with a vector. I'll show you how a lot of things that you do can be reduced to multiplying a matrix with a vector. Then I'll go into the guts of MapReduce and tell you how things don't work very well when you multiply a matrix with a vector. Then I'll talk about a sequence of optimizations. I'll talk about how you can, this whole reduce operation that happens every once in a while, which causes all of this slowdown, how you can get rid of it by asynchrony. Then I'm going to talk about how, even if you have asynchrony, you really can't program very many different operations. So I'll talk about many algorithms that require speculation. And I'll talk about how you can do speculation in MapReduce, and when you do speculation in MapReduce, really bad things happen. Okay, and then I will use that to motivate why you should execute your maps as transactions. Okay, and then I'll start to talk about a system called TransMR, which is transactional MapReduce, and then I will talk about how things go tremendously wrong in transactional MapReduce, because at some point you have to commit the transactions, and when you commit the transactions, there's a whole bunch of nested locks that happen. Nested locks are tremendously bad in distributed systems. And I'll talk about how we should actually be doing locks. But in the end, I will leave you with a sense that what I've given you is a whole bunch of engineering solutions. The real problem pretty much stays. Okay? So let's start simple. How many of you know what PageRank is? Excellent. Almost everybody knows what PageRank is. So if you remember your early papers by Page and Brin, think of a PageRank as something that a random surfer would do. I don't know how you guys surf, but I have a certain homepage. My homepage happens to be, it's called Huffington Post. It's a sort of a left-leaning newspaper or online newspaper. So I start from Huffington Post. I'll follow a few pointers. I get lost at some point. I'll come back to Huffington Post. I'll chase some more. Well, at some point, I'll say, fine, let me go to Bloomberg. I go to Bloomberg. I will chase some more from Bloomberg, come back. Typically, my third thing is New York Times. I'll go to New York Times, chase some more, come back. So this tells you how a random surfer works. So a random surfer has an initial vector. These are a vector of preferences. My preferences happen to be Huffington Post, New York Times, and Bloomberg. And essentially, I do a random walk from these initial set of preference pages. And I keep surfing, okay? And I keep surfing. And with the probability mu, I restart, which means I'll come back to my preference. I'll select from my initial preference vector again, and I keep surfing, okay? And if everybody plays this game, essentially what you can do is to say what is the probability that anybody will be at any one page, okay? And the higher the probability, the more important that particular page is, and this defines the page rank. Okay? So page rank can be cast as a power series representation. Once again, you can simply write this as essentially a column stochastic matrix X. Think of this matrix as your graph, your web, and I made it column stochastic by normalizing all the columns. And really, every time you take a step, you multiply it by S again. So essentially, it's the sum of all the probabilities, which means that you get this polynomial, and the polynomial looks like this. Okay? So this is page rank, nothing deep. In fact, page rank is simply the eigenvector of the column stochastic matrix that we're talking about. Okay? It turns out that you could actually you can do other kinds of ranking as well. Page ranks is just one example. In fact, there's a much more general approach called a functional ranking. There's nothing sacred about this polynomial. You can define any polynomial you want. Okay? So I could define any of these SJ matrices, and they're all scaled. Ideally, you'd like for them to dampen out as you go away from your starting point. And it turns out that page rank is just one example of a functional ranking, and I could have written this page rank as this special case where the damping factors are given by this. Okay? People don't normally use functional rankings. Functional rankings are tough to design, they're hard to implement, but nevertheless, you can do fun things with functional rankings as well. So this was a fun little result. Let me just ask you, if I were to ask you how to compute page rank, how would you do it? And I said I didn't necessarily care about the exact page rank. Give me some sense of what's going to be on the first 3 pages of Google. What would you do? So about a year back, what I would have done would be to start a random process, or at least get some estimate of the eigenvector. Okay, the eigenvector, that was just the power method for computing the eigenvector. I just get some estimate for the eigenvector. So you're taking a random process, you're essentially running the random process over the entire graph. So that's one way of doing it. It turns out there's a much better way of doing it, where instead of running one random process, you run a very large number of random processes. Okay, you run as many random processes as there are nodes in a network. So if there are 1 trillion nodes in the network, you run 1 trillion random processes, and instead of running a much longer random walk, you run a much shorter random walk. So now you have 1 trillion surfers, each of which is only doing a random walk of length 5, let's say. Okay? And every time a surfer goes to a node, it drops a token. And all you have to do is to count the tokens. Okay? And I can prove to you with very high probability that this extremely short but large number of random walks will pretty much give me the first few important pages in Google anyway. All right. So it turns out that this was a neat result, and one of the things we were looking at was, can you do this for any functional ranking? It turns out we show this really neat equivalence where you can give me any polynomial on a matrix, and I will reduce this to a product of matrices as opposed to a polynomial on matrices, and that the product is such that the product matrices have the same non-zero structure as the original matrix, which means that I can still do this multiple random surfer model, and I can get much faster functional rankings. Please. So functional ranking is a general polynomial that you can define. Okay? So functional ranking is, you can simply say my ranking is given by, let's say A is the matrix of your graph, the column stochastic matrix. It is A times some initial vector plus 0.3 times A squared times V plus 0.11 times A cubed times V. Okay? I've just come up with this. You can come up with this. You can come up with whatever polynomial you want yourself. And in fact, these are I'm sorry? It's not random. In fact, you build a lot of intelligence into these polynomials. So there's nothing sacred about page rank. There's nothing sacred about this polynomial. Mind you, this polynomial simply is a times v plus a squared times v plus a cubed times v and so on. Okay? And that just happens to be one polynomial which Larry Page thought was a good polynomial, and people use it. But in fact, you could do something much smarter. This is where your intelligence is. And if you could design these well, you could make your rankings look very nice, much nicer based on what your graph looks like. You could certainly do that. The reason people don't do it is because these are hard to find. How do you design these? And these are hard to implement. And in fact, this result that I'm showing you really is essentially that I can run the same process of multiple walkers, and I can get these functional rankings just as quickly as you can get page ranks. Okay? So that's a very neat result. It's a very powerful result. It's a neat result. It's called multidamping. Okay? So this was one of the starting points, and we were running these things on really large machines, and we were seeing lots of overhead in running these things. I'll skip this result. This result simply says that I can essentially run any random ranking, and I can get you the top ranks extremely quickly using this multiple surfer process. All right, so this is another example of what you might run on large MapReduce clusters. So I've given you two graphs here. Here's a red graph and a blue graph. You could think of this as Facebook and Facebook. They don't have to be two graphs. This could just be the graph and itself. And I'm asking you this question: what are topological features in one network that map very nicely into corresponding features in the second network? Okay? So generally, this problem is called graph matching, graph alignment. First you align and then you match. Okay? It turns out that the algorithm for doing this, one of the algorithms for doing this, is actually very closely related to what you would do in PageRank as well. So if I were to ask you how similar are these two nodes to these two nodes, the question can be answered by simply saying, well, the similarity of this and this with respect to this and this is determined by the similarity of the neighbor here and the neighbor here and the neighbor here and the neighbor here. Okay? In other words, two nodes here are as similar to two nodes here if they are joined to other nodes that are similar to each other in the network as well. Okay? So notice that all I did was I took PageRank as it was defined on one. Remember what PageRank is. PageRank simply says that I have high rank if my neighbors have high rank. Okay? So I've now just done this on two networks. I simply say that two nodes line up very well with two nodes here if their neighbors line up very well as well. Okay? So I could write this thing in this little thing. Don't be intimidated by the math. All this says is that there's something called an initial similarity of nodes. If these two nodes had a prior, I knew that these two nodes were similar. So you code the prior in this particular matrix, H, and this is the topological similarity. This simply says that the similarity of a pair of nodes is determined by the similarity of their neighbors as well. Okay? So this is called isorank. You can use this for computing similarity of nodes in networks. Okay? Turns out this is actually tremendously hard to compute. The reason this is hard to compute is this is an iterative process. And in the second iteration, what you're trying to compute is a matrix X. Okay? So the size of X is equal to the number of nodes in the first graph versus the number of nodes in the second graph. The ijth entry of this X will tell you how similar node I in one graph is to node J in the other graph. Okay? So this is what you're trying to compute, and you're trying to compute this iteratively. And the problem with this is that in the second iteration, X becomes dense. If X becomes dense and my graphs are both a billion nodes, that's a billion by billion dense matrix. You're never going to do this. You can use the biggest machines, you'll still never do it. Okay? So you can't do this. This iteration is not workable. Okay? So the question is, how do you do this? It turns out that you can actually do this very neatly as well. And this is a result that we had a couple of years back, where if you just expand this out to n iterations, no magic here. All I've done is I've taken this iterative process and I've expanded out the matrix. This is xn, which is the nth iterate, and I've written this out this way. All I have to do is to take the initial matrix of similarities, express them as an outer product, and what happens is the entire iterate can now be written in this form. I won't go into the details of this, but the beauty of this equation, equation 2, is that I have no matrix operations anymore. Everything is now multiplication of a matrix by a vector. Okay? What that now lets me do is that I can actually compute similarities on very, very large networks. Okay? So in fact, these are just some networks that we mess around with, relatively small networks. We do this on much larger MapReduce clusters for much bigger problems, but this just happens to be relatively controlled, but still fairly large. So if you take these two large, that's a story for another day. These are protein interaction networks. This one's got about 10,000 nodes. That's a protein interaction network of a human cell. And the next biggest is fruit fly, which has got about 7,500 nodes. So you would imagine that when you try to line up these two nodes, you end up getting that X matrix, which is very large. And in fact, if you look at this accelerated algorithm, that is in fact the slowest one. It takes about 8 seconds, which is really nothing. But if you were to run the base iteration, it takes about 8,000 seconds. And that difference only grows. So what this tells you is that I can actually run very, very large networks, and I can line them up with each other. So I can take something like Facebook, which has got about 1 billion entries, and I can line Facebook up with itself. And you can find out who is that other person on Facebook who is topologically the most similar to you. Okay? So there's something actually fun here. Computing these alignments is in fact exactly the same as computing page ranks on the product of the two graphs. So I could take the two graphs, I could compute the product graph, and if I were to compute the page rank on the product graph, that would be the most, that would be the highest ranked alignments of the individual networks as well. But that's a story for another day. So we can do that perhaps another time. Anyway, so You can do this. You can run these on both parallel platforms. You can run these on MapReduce platforms. In fact, the largest graph we ever processed here was over 1 billion nodes and 20 billion edges and on a fairly large MapReduce cluster. So we know how to do this. We see the overheads in doing this. All right, so let me now come back to MapReduce, and I will tell you where you get stuck or where the problems are with doing something like this. How many of you know how MapReduce works? So let me go through the basics very quickly. So MapReduce has two phases, map and fold, or map and reduce. And a map is essentially a function, and you can apply this function to a bunch of key value pairs. It's a function that can be independently applied to each key value pair. So I'm going to give you a list of key value pairs, and I'm going to apply the same map function on each of these key value pairs. And when I apply this map function to this key value pair, there will be an output key value pair that comes out. Okay? So K11, V11, you apply map 1, and you get K11 prime and V11 prime. Similarly, you do this here, you do this here. So if I give you a long list of 1 billion entries, you apply the map function to this billion entries, you get another billion entries out. These are the output key value pairs. Okay? So why do I have to consider this as key value pairs? It can just be one value. So spoken like a true programming languages person, there's no reason to think of these as key value pairs. These people just think of these as key value pairs. So they don't even call it fold, they call it reduce. So they have their own terminology, but there's nothing that restricts it to key value pairs. So these are the maps, and the only other operation that is available to you is a reduction operation. And what the reduction operation does is it takes all the like keys that are coming out of these map functions and applies a reduction operation on them. Okay? So if this K11 prime was the same as K21 prime, the key was the same, then it would apply a reduction operation on V11 prime and V21 prime. Okay? So once again, what will come out is a key value pair again, where the keys are all unique now, and the values are all the reduce function applied to values corresponding to the original keys. Am I making sense? Have you ever thought of why somebody would think of such a harebrained way of programming? Why would you restrict yourselves to such a constrained way of writing programs? Please.
So that they can be distributed over a number of nodes.
But there's other ways of distributing too, right? Why this extremely restrictive framework? So the reason they did this is, or the reason Google did this, was they would have these really large data centers, and they would do maintenance, they would hot swap disks and things like that. So at random times, machines would go down. So when they were computing page ranks and what have you, they wanted to be prepared for an environment where arbitrary machines could go down at arbitrary times. So fault tolerance was their primary objective. Okay? So when you're doing fault tolerance, the most obvious way to do fault tolerance is checkpointing. Okay? But you don't want to write an arbitrary distributed program and try to do a checkpointing because you can't find a consistent checkpoint. Don't worry what a consistent checkpoint is if you don't know. But nevertheless, checkpointing large distributed programs on 100,000 machines is hard. Okay? So you have to have a way of checkpointing. So what happens in this particular thing is actually quite nasty. Okay? So when these key value pairs come out of maps, they're actually written to disk. Okay? Typically not just to one disk, but to 3 disks. Okay, or please.
What is the input? Is it one key value pair?
No, it's a list of key value pairs.
For each box?
So think of this as a billion instantiations of the same function, and so you will have 1 billion key value pairs. One of them will come to each of those instantiations, and what comes out is a key value pair.
The output has multiple pairs.
Well, so in this particular case, actually it could also be more than one. I'll give you an example where there's one pair, or the outputs can be multiple pairs as well. So I'll give you an example of shortest path, where what you're doing is the key value pair is the cost associated with a node, and what you're generating is key value pairs associated with every one of the out edges of that particular node.
In this case, each box, what is the input and what is the output?
So the input is one key value pair coming into each instance of the map, and the output is one or more key value pairs coming out of the map function. And the reduction, once again, takes all of these things, clusters together all the keys with the same value, and then applies the reduction operation on it. Okay? And the only reason why this was all done was at all of these points, there's actually an implicit checkpoint. There's actually a disk write that happens. There are multiple disk writes that happens, which makes this tremendously expensive. So you will see milliseconds of delays between these things, simply because this thing is going down into either HDFS or GFS, depending on the file system that you're. If you're using Hadoop, it goes down into HDFS. If you're using MapReduce, it'll go into a GFS cluster. Okay, so these are writes that happen to disks. All right. So this is really, if you do any parallel computing, this should be fairly clean to you. So what is happening is I'm going to take a bunch of these are the key value pairs coming in. I'm going to group them first, split 0, split 1, split 2. I'm going to apply the same map function to all of them. I'm going to generate a whole bunch of key value pairs here. And essentially, effectively, now I have to do a join. Okay? And the way I'll do a join is I'm first going to group all the local keys with the same value and apply a reduction operation. Okay? So this is essentially a local reduction operation. But then I have to do it globally, because that key value might have been here as well. The same key value that's here might have been here as well. So the next thing that happens is a hash. So this happens over the entire network. So all the like key values will end up at the same reducer. These are called reducers. And the reducer will then globally match all the key values and apply the reduction operation here. So the reason you do this in 2 steps is because you don't want to hash everything. Hashing everything will clearly take a lot more communication. You want to do a local reduction first and then do a global reduction. So you can set all of these things. You can set the number of mappers, you can set the number of reducers, but this is essentially your programming environment that you're programming MapReduce in. All right. Let's do some simple things in MapReduce. It'd be quite counterintuitive, but you can do things like, spelling mistake here, simple shortest path. Very simply in something like this. So the map operation here doesn't actually do anything. So in this particular case, the map operation, the key is the node ID, and the value is the adjacency list. Okay? And what it's doing is, for each edge in the adjacency list, all it does is it outputs the destination ID of that particular edge and the distance of the source plus the edge weight. Okay? So you'll see that this is an example of something that's going to take in 1 key value pair and generate a large number of key value pairs coming out of a single map instance. Yeah, it's a single source shortest path. So, but this is the operation that will happen constantly on the inside. Okay? And the reduce actually is very simple. All it's doing is it's going to take a node and a distance list, and it simply compute the minimum of the distance list and assign that to that particular node. Okay? So you will notice that this is a MapReduce program for computing single source shortest path. Extremely simple, okay? And it works nicely. And the core program simply is, while not converged, run MapReduce job, and that's the job that you're running. So you can write these things very easily. I'll call this naive mat-vec, okay? So once again, all I've done is it's a matrix vector product. You're taking the matrix of the graph, you're multiplying it by the vector. I've just changed the operations. Instead of doing an addition, I'm doing a min, and instead of doing a multiplication, I'm doing a plus. So in a matrix vector, if you do this change of operations, the single source shortest path simply becomes a sequence of matrix vector products. Okay? So I'll call this a naive matrix vector product. Map takes an adjacency list as input. I don't know how many of you used Pegasus, but Pegasus is a graph library that CMU has. And Pegasus, the Pegasus implementation of exactly this, reads 1 edge per map. So if you think of this as a matrix, Pegasus does a 2-dimensional partitioning of the matrix. Simple mat-vec that I'm talking about assigns nodes to maps, which means that it's a 1-dimensional partitioning of the matrix. All right. So this is very cool. If you think of what I explained it happens in this process, you will see exactly this happening in real time here. So this is percent CPU, this is network I/O, and this is disk I/O. So you will see that initially the mappers are working. So the CPUs will show you some high utilization. But after a while, this is where you're doing the hashing. So you see lots of network traffic. This is where the hash happens. And then you see all of the commits happening from the 3 copies that happen at the reduce point. And you see a tremendous amounts of disk I/O. And most of it is block out. So this is where the writes are happening on the reduction operations. And once again, remember why we were doing this. The reason we were doing this was just to make sure that I had fault tolerance. The idea here is that after I've done the reduction, in the next sequence of maps, if some of the maps fail, I assign the maps to the runtime system of MapReduce, assigns the maps to a computer, and somebody just takes down the computer. the runtime system always keeps a heartbeat, and it determines that this computer has gone down. It can simply reschedule the maps that were given to this computer. It never actually has to go back before the previous reduce, because the reduce has been committed. Okay, that's the reason why this whole thing is set up the way it is. All right, so let's go through the simple processes of optimizing this. So if you're looking at what happens, the map time really is quite small. It's only 20%. There's the spill, which is about 40%, the merge, which is about 20%, the shuffle, which is the hash, which takes the most time here, and the reduction operation is about 30%. The sum of these things is in fact more than 100%, simply because there's some overlap in the stages.
So what exactly is the spill and shuffle? Like,
So what happens is the maps are actually done in stages as well. So what you do is you read from disk in chunks. So in GFS or HDFS, the chunk sizes are about 64 megabytes. So what you'll do is you will read 64 megabytes worth of key value pairs. You will process them, and you will write them back. So that's the spill part. This is the local reduction. This is the hash, also called a shuffle. And this is the global reduction. Okay? So this really is what happens. And the sad reality of this is this, and to some extent these, were my only computations. Everything else is overhead. So this is the reason why you'll see significant slowdowns in MapReduce programs if you ever try to write a MapReduce program. Should not be discouraged. It's simply the reality of MapReduce programs. All right. So let me now do the first obvious thing, which is that instead of applying each map to one node, I'm going to first partition the graph itself. So I'm going to take my million node graph, and I'm going to break it down into a large number of partitions. Okay? This is subgraph size and powers of 2. That's 2 to the power of 18. So each partition is now 2 to the power 18 nodes. Okay? And I'm going to treat this as one map task. Okay? And by doing this, I've built granularity into this thing, which means that all the reductions that have to happen will now happen within the map task itself. So essentially what I've done is I've grossly reduced the traffic that goes to the hash phase or the shuffle phase. Most of the traffic is taken care of in the local reduction itself. Okay? And simply by doing that, I can reduce the time fairly significantly. Essentially from 255 or thereabouts to about 225. What I've done is I have essentially zeroed out the global hash part of this particular computation. Okay? Yes, it reduces the parallelism, but the assumption here is that your graphs are so large that you will never have a billion mappers anyway. Yeah. So you will have a few thousand mappers. You have a graph of a few billion nodes. So you still have that concurrency. All it says is that build the granularity so that you do most of the reduction locally, don't do global hashes. So this actually also neatly tells you what my hashing overhead was. I've essentially zeroed out the hashing overhead for you here. All right. It turns out that if you run this thing on EC2, you actually see fairly nice speedups. And actually, we were quite surprised here. In this particular case, you will notice that the naive implementation is in fact much better than the Pegasus implementation, and that's a log scale. So you're seeing a 10x improvement, 10 times improvement in performance over a fairly credible implementation of these things, simply by doing some very obvious optimizations on these things.
the shuffle time is the network delay.
Yes, the shuffle time is the hash time.
Is that the network delay?
That's the network delay mostly, exactly, yeah. And the problem is the network delay actually somewhat exaggerated by the fact that the messages are very large. So when you're sending these 100 megabyte, 200 megabyte messages, the routers mostly back up. So the network delay on large messages is very high. All right. So now let's do the next optimization, which is that you have these very strongly synchronized steps of map and reduce operations. Maybe we don't need these very strong synchronizations. Turns out things like PageRank are actually very tolerant to asynchrony, which means that if I were to give you one part of your graph, you can compute the PageRank locally for a good long time before exchanging the PageRanks of the border nodes with the next person. And you can do that much less frequently, but for the most part work with it. All right, so let me talk about that. So here, what I'm now trying to do is to synchronize once every few iterations. And what I'm going to do is to rewrite my MapReduce. So remember in what we were doing in PageRank, we would compute a mat-vec, and everybody would finish the mat-vec, and then we would issue the next mat-vec. So essentially, when I'm trying to compute a to the power n x, I'm trying to write that as a times a to the power n minus 1 x. And until I compute a to the power n minus 1, I can't compute a to the power n. So what we're trying to argue here is that you don't have to do that. You can compute these fairly loosely.
Shortest path, the reduce has to synchronize until all the.
No, you don't. That's the point.
But in the naive scheme.
In the naive scheme, yes. In the naive scheme, you do.
All the sources are ready.
Absolutely. But in the relaxed scheme, you have an outer iteration which says that keep doing this until you're converged. So if I have, for example, 4 in paths, I can simply take 3 in paths, update my cost. And that might not be the correct cost, but the outer iteration will make sure that that becomes the correct cost. All right. So what I'm now going to do is to have a 2-level MapReduce. I have a local map and a global map. And the global mapper makes sure that there's a global synchronization and a global convergence. All right. So this is what the basic MapReduce looks like. This is what a local global MapReduce looks like. These are local mappers, or these are local MapReduce operations, and this is the global MapReduce operation. I'm going to skip some of these details simply because I want to get a second part of the talk, which is perhaps more interesting. So I'm going to give you some examples of relaxed synchronizations here. This was a single source shortest path we were talking about, but you could also do MST, transitive closure, etc., mat-vecs, and I'm going to show you the results on some small number of EC2 machines. And they're small simply because I realized I let my students run this for a month, and in 1 month they run a few $1,000s worth of bills on Amazon, which is not a good idea. So I said, fine, just run it on the small numbers. So the blue is the general single source shortest path, and the red is the relaxed single source shortest path. And here I'm simply showing you the outer iterations. I'm not showing you the inner iterations. There's a large number of inner iterations, but I'm only interested in the outer iterations. And you will notice that the outer iterations are in fact significantly reduced, which is not surprising because I have hidden from you the cost of the inner iterations. Mind you, what's happening now, I'm taking a little part of a graph, I'm doing a whole bunch of inner iterations, and periodically I exchange the outer information data, okay? But notice what happens to time. Time almost completely tracks the outer iterations. What this tells you is that you're almost spending no time in local mappers. The overhead almost entirely is in the global mappers, okay? So this is fantastic, right? You've done absolutely nothing. You've taken a global synchronized scheme, you've reduced it to a locally synchronized scheme, and you've reduced your time by an order of magnitude just by doing that. You're getting exactly the same results, okay? So this is very neat. So I'll skip this. The takeaway is exactly the same. Let me now get to the third optimization, which tends to be more difficult and more fun. So this is speculative parallelism. So for many applications, it turns out that the concurrency is not known a priori. Okay, you're trying to do something like Delaunay triangulation. You're trying to do some types of minimum spanning trees, things like that. You might have multiple nodes trying to update one node all at the same time. Okay, and this depends on the graph structure. And since you don't know this a priori, the concurrency in these computations is very limited. So a couple of years back, a friend of mine, Keshav, wrote this paper where they talk of this as amorphous parallelism. Okay, so this is parallelism that is only manifest once you see the data. And this is also a classic example of where software transactional memory comes to fore, where they say that the only way, or one of the reasonable ways of getting concurrency out of such computations is by treating them as transactions. And so let's say you have a transaction here that is trying to color a node. You have another transaction here that may or may not be trying to color this node. You let both of the transactions go through. Most of the time, there'll be no conflict. If there's no conflict, you have concurrency. If there's a conflict, you detect the conflict and you have to roll back. And so long as the number of rollbacks are not significant, you get excellent performance because for the most part, you're not hitting any conflicts on these transactions. So this is the thesis of software transactional memory. It has its upsides, but really it never lived up to its initial promise, mostly because software transactional memory is very expensive. So the overhead of detecting conflicts in transactions and rolling back these conflicts tends to be very hard in fine-grained systems. Okay, turns out these are not fine-grained systems. You can actually run transactions in these things quite easily. Please. So let's take an example where the graph is exactly the people sitting in this room. Okay, so let's say you're trying to do coloring. Okay, so let's say your color is red and your color is black. Okay, and we're trying to two-color this graph. Okay? If your color is red, your instinct would be to color him black. Okay? Since your color is black, your instinct would be to color him red. Okay? So you write a transaction which says, color my neighbor red. You write a transaction, your transaction says, color my neighbor black. Okay? You don't know that the two of you are trying to color the same person. So you let both of those transactions go through. Okay? And you will realize that at that particular, he will realize that there are two people trying to color me different colors. So he will send both of you a message back saying, hold off guys, back away, something has gone wrong here. Okay? So that would be an example of a conflict. But as you might imagine, most of the time there might be no conflict here. So if there is no conflict, if he was not trying to color something at this point, there's lots of concurrency. Each of you could be coloring your neighbor, and for the most part, everybody's color goes through. You have lots of concurrency. And so the whole point is you want to minimize the conflict. So that's an example of where this might happen. All right. So to do this, I now have to do two things. MapReduce itself has no shared context. What that means is one map function, one instance of a map function, has nothing to do with another instance of a map function. There's no shared data structure between these two. They work in their own spaces. So the first thing I have to do is to get some kind of shared data space underneath these two maps. The second thing I have to do is to build all of this infrastructure where I can issue these things as transactions, detect conflicts, roll back conflicts, and do all of the other things that I'll tell you that you'll end up having to do. Okay? So the problem here is that what I'm going to do is to use a key value abstraction of a storage called HBase. So I'm going to run maps on top of HBase. So HBase is a disk resident key value store, and each map can read or write from HBase. So this gives me the shared address space that I want. Well, the only problem is I now have a problem because when maps fail, maps are rescheduled, which means that there's always a runtime system which is looking at the heartbeat, and if I'm halfway through the map and it detects that this map has failed, it'll simply pull, or of course this one is gone, it'll replay the map on another machine. Okay? But the problem is if you're running maps on top of HBase, HBase is persistent storage, which means that if you're halfway through that map, you might have done a whole bunch of writes onto HBase, and if you replay it, your semantics are gone because you have no idea where you stopped and you're just replaying the whole map. Okay? So this is a problem. And the solution, the obvious solution here, is that map and reduce operations should both be executed transactionally, which means either the whole thing happens or none of it happens. And if you can guarantee that maps and reductions are only executed transactionally, then you can guarantee that the semantics of the MapReduce operation on top of HBase is not violated. Okay? So the question is, how would you then, please? Oh, it's the same thing. So HBase is just an example. We happen to be using HBase, but the same issues would happen with Cassandra and all of the other key value stores as well. All right. So now my abstraction looks something like this. I have a whole bunch of computational units that are working on some local stores. So think of these as machines. These are running maps. And this is the local store of the machine itself. And there is some distributed key value store that is sitting underneath this thing. Nothing fancy. Okay? And my operations are simply this: put and get. Okay? I'm going to rely on optimistic reads and buffered writes. Okay? The local store forms the write buffer for my computation. So when I execute a map, the local buffer is going to maintain all of the local variables. Okay? So when I do a put, it writes to the local store, which is later atomically committed to the global store. This is important. It's atomically committed after you validate it. Okay? When I do a get, it returns from the local store if it's already present. Otherwise, it fetches from the global store and stores it in the local store. Okay? There are other operations, but these are any thread local operations. So I don't know how many of you know what software transactions are, but in software transactions, there's a notion of a read set, there's a notion of a write set. These are all the things that are going to be used inside of a transaction. You're going to read all the items in your read set. You're going to do whatever computation you want. And when you're going to write items in your write set, you have to validate to make sure that there are no conflicts on the transaction, and then to atomically write all the items in your write set. All right. So what we use is what is called optimistic concurrency control instead of pessimistic locking. And the locks are acquired at the end of the transaction. Okay? So the write buffer and the read set of validating is those are the concurrent transactions, assuring serializability here. The client potentially executes on the slowest node in the system, and therefore pessimistic locking essentially will slow down everything. You don't want to use pessimistic locking here. For those of you who are into databases and who know what the CAP theorem is, what this does is it focuses on consistency and tolerance to network partition over availability. Okay? I'm going to skip some of these details. I'm going to show you some results. I'm going to show you why the results are bad, and I'll come back and fix them. Please.
So you said you detect the end of transaction. So how do you do that?
So what happens is, so let me take a slight sidebar here, and this will set up my problem better as well. So HBase gives you single key transactional semantics. What that means is that when I read or write, it will only give me transactional update to a single key, okay? And everything is time-stamped, okay? So whenever I do a write, I see a timestamp. So let's say the two of them are playing the same game here, okay? So he has read his color, and he's trying to write something back into his color, okay? He's playing the same game here. Now when he reads, he gets a timestamp on the read. When he writes, he updates the timestamp on the write. So when he does the commit back on the color, he can look at the timestamp and he knows that the timestamp on the right side, on the read side has changed, which means that there's a conflict on the transactions, and he quashes the transaction. Okay? All right. So let me skip a little bit, mostly because please. Pessimistic locking simply means that if I'm going to lock everything in my read-write sets, execute the transaction, and I'm going to write them. Okay? So you don't want to do that is what I'm trying to argue here. All right. So this is a minimum spanning tree algorithm. This is called Boruvka's minimum spanning tree algorithm. And once again, what you do is you have these local spanning trees that you compute, and you're trying to merge these local spanning trees. And the merge operations are executed as transactions. You want to make sure that people are not merging into cycles. That's what you're trying to make sure here. So if you do this, there's no concurrency in the base program itself, but if you execute these speculatively as transactions, you actually have significant concurrency, and you see a fairly significant improvement in performance, not as much. You get about a 4-fold speed up on 16 nodes. You should be somewhat surprised by the lack of performance here. The interesting thing also is that as the number of processors increases, the number of aborts also goes up significantly. The aborted transactions that I was talking about when multiple people trying to write this, as the number of nodes go up, you will see that these are the number of aborts. The number of aborts goes up as well, which is somewhat expected. There are other examples. This is MaxFlow, and MaxFlow has a similar behavior. You get about 4.5-fold improvement in performance, and you see the same behavior. Time goes down, aborts go up. This is what is causing the problem for you. All right? But let's look at what happens at the back end of this computation. So here's a transaction. It's gotten everything in its read set. It's done all of this work. And now it's trying to commit at the back end all of these things. It's trying to validate the transaction and trying to commit. And how do you do this? Remember, this has to be done atomically. So let's say I'm trying to write 5 things at the back of my transaction. And since HBase doesn't give me multi-key transactional semantics, what that means is that there is no operation called multi-put. If there was an atomic operation called multi-put, I could write 5 things into HBase. There isn't such an operation. So the question is, how do you implement a multi-put in HBase? So essentially the way I would do this is using locking operation. I'll pause at this point and I'll pose a problem that I do not know how to solve, which is that in all of these distributed computations, the lock state is somewhat sacred. Okay? So you have a computation that is running. Some things are locked, some things are not locked. Okay? And it's extremely important for you to know exactly what is locked and what is not locked. It turns out this is tremendously expensive. So for those of you who program systems at scale, the lock state is typically maintained using Paxos. So Paxos is a consensus algorithm. So what they will do is they will have 20 machines running Paxos, and every lock state you run a consensus algorithm. You determine whether all of us agree that something is locked or unlocked, and once you've agreed that something is locked or unlocked, that becomes a lock state. But the overhead of Paxos is tremendous, and therefore locking in distributed systems becomes tremendously expensive. An alternate way of doing locking, which a lot of people do as well, is essentially to treat locks as one more column in HBase, in your key value store. Okay? And since I know that HBase gives me single key transactional update, I can do a lock or unlock on one lock relatively quickly in HBase. And when I say relatively quickly, it's still slow, because remember, HBase sits on HDFS, which is the file system, and HDFS itself makes 3 copies. So the way lock state is maintained in a fault-tolerant fashion in this is by making 3 copies of every lock that you have. And mind you, these 3 copies typically, once again, for those of you who don't do HDFS, the first copy is your local machine, the next copy is a machine in your data center, the third copy is in a remote data center. And that's to tolerate network partitions. Okay? Yeah. No. So I'm trying to tell you 2 things. One is the complexity of multi-put, and the second is the complexity of a single lock. So let's say you're trying to put V1, V2, V3. These are the 3 values you're trying to write. So the way you would do this atomically is to get a lock on V1, get a lock on V2, get a lock on V3, conceivably get a token number. You can actually do the data update asynchronously, get a token number, and then unlock. So this is what we would do. And I will focus on the overhead of that operation. But even before I do that, I'm trying to focus on the operation of just one lock itself. So when you try to do a lock of V1, what you're trying to do is to atomically set the value of a variable from 0 to 1. Okay? Now if you're just trying to set the value of one variable in HBase from 0 to 1, now HBase sits on top of HDFS. Okay? Which means that all data here is 3x copied. I have to do that to make my locks fault tolerant. I want to maintain my lock state in a consistent fashion. Okay? And the way you maintain 3 copies of just that one variable, which is 0, 1, is by something called chain replication, which means that data is not assumed to be consistent across all replicated copies until you start from the master, copy it to the secondary, copy it to the tertiary, and then the tertiary acknowledges the primary. So when you say AI equals 0, where A is an HDFS resident data, this causes at least 3 networks, actually 4 network delays and 3 disk writes. So you can imagine AI equals 0 is tens of milliseconds of overhead. It's on one lock. Okay? Now you have to do a large number of those locks for your multi-put operation. Okay? So this is a tremendously expensive operation. And there is really no way of getting around it. Paxos is expensive. This kind of lock replication is expensive. So what people are now looking to do is to see if you can use SSDs or flash memories and persistent stores on machines and use SSDs to maintain lock state and get fault tolerance through those. But those are solutions that are not available yet. But nevertheless, let me talk of this problem where I'm simply going to do a sequence of nested locks and how difficult even that problem is. All right. So transactions are costly at large scale. There's two-phase locking, two-phase commit, and I'll tell you what the overhead of these things looks like. So this is what we were talking about. You start, and this is the back end of the transaction. You do a lock on L1, lock on L2, lock on L3, do a busy wait if any of these are taken. Once you get all the locks, you can essentially get a token number and continue with the transaction after it's validated. The question is, how do you do this? Okay? It turns out that I was shocked that this is actually a relatively complex operation. If everybody is playing this game, if there are significant skews in lock accesses, it turns out that the order in which you obtain these locks significantly determines performance. Okay? So if you have a Zipfian type distribution on the locks, and if I have this busy wait locking protocol, it can be multiple locking protocols, right? You could come up with your own locking protocol where you catch the first lock, you do a try lock. If it's available, you take the first lock. You do a try lock on the second lock. If it's busy, you actually relinquish the first lock as well and go back to the back of the queue. So that's one locking protocol. The other locking protocol could be you do a busy wait on either of these. So these are all different locking protocols. Turns out that if this is the locking protocol that you're using, as you might imagine, you want to catch the most contending lock at the back end of this queue. Okay? Because you want to hold the most contending lock for the shortest period of time. Okay? Turns out that if you're actually going to relinquish the locks, you want to catch the most contending lock first. Okay, and just by doing this, you can actually get significant improvements in performance. Okay, now of course we have to be really careful here because there are multiple people playing this game, and all of their lock orders must be consistent. If their lock orders are not consistent, you end up with deadlocks. Okay, so let's say you have what we call strong, strict two-phase locking. This is strong, strict two-phase locking, and this is the waiting case. And the lock acquire stage is the only sequential stage. The other stages can be parallelized to finish in a single round trip. Okay, so what we do is what is called contention-based lock ordering, which is that order the locks so as to decrease the total amount of waiting time. And for the waiting case, the lock with the least contention should be acquired first. The lock with the most contention should be held for the smallest amount of time, so it should be acquired last. It turns out you can actually do more fun things as well. This is something that has only been superficially tried in parallel programs. So there was a paper back in the mid-80s, I think, where somebody tried to do this on POSIX or some threads program. POSIX didn't exist as a standard back then, but they tried to do this on a threads program where they were trying to coalesce locks. So think of these as, if in today's POSIX programs, you're doing pthread lock, pthread mutex lock, pthread mutex lock. This is a sequence of nested locks, and the question is, can you merge some of these locks to reduce the nesting depth of these locks? It's hard to do in POSIX programs because the overheads are so small. It turns out here you can actually do these very nicely. So you can take these locks and you can group them, and once you group them, you can assign these groups to a fairly small number of groups of lock servers. So now what you're doing is you're creating a new HDFS table. You're restricting the HDFS table to a much smaller space, and you're assigning these locks or lock groups in such a way that the lock accesses over these small number of HDFS machines is both load balanced and minimizes contention. So I'll quickly go through some of these results. It turns out you can actually do some fairly nifty things where you can think of every transaction as a clique. So if I'm trying to do a multi-put on K1, K2, K3, K4, then think of this as a clique of K1, K2, K3, K4. You can sprinkle these cliques over all of your keys. What you get is a graph that looks like this. You can then partition the graphs, and this partition of the graphs will then give you the partition of locks, which can then be assigned to a fairly small number of lock servers. There are a number of fairly sophisticated protocols involved because what you're now doing is a whole bunch of lock caching and lock flushing, and all of these things themselves have to happen transactionally. But once you get that right, you can actually get very significant improvement in performance. So that's something that on a benchmark gets reduced from something like 550, 600 to roughly about 100, 150. Please. So the lock partitioning is actually very tricky because everybody has to agree on the lock partition. So what happens is that it's not upfront, it is dynamic. So what we do is we constantly monitor what locks are being accessed together, and we redo the partitions. And what happens is that if you make a mistake in trying to access a lock partition from a different server than where it's actually at, it actually doesn't return a wrong state. It causes a performance overhead. Okay, so long as we're all agreed on the lock sequence, it doesn't cause errors. It causes performance problems.
The consensus on updating the logs has now been replaced by a consensus on the log groups. Still in consensus on
Okay, so actually we get away from the consensus-based protocol because we're using a replication-based protocol. So yes, if you were using Paxos would now be run on log groups as opposed to locks.
you said you need consensus on what the log groups are. Everyone has to agree on that.
Sure, so that's a different, I mean, that is for deadlock reasons. So we all have to agree that we're going to use these log groups and we will acquire these log groups in this order. Because if we don't do that, we will get ourselves into deadlocks. Because if you assume that L1, L2 are in one log group and you assume that L2, L3 are in one log group, the fact that you access those different log groups potentially causes deadlocks. So that's for deadlock reasons. The consensus for agreeing whether a certain log group is in a locked or unlocked state is for the fault tolerance reasons.
That is done using the
I'm sorry?
That is still done using the standard.
Exactly. That's still done using exactly the same thing. You could do it using Paxos or you could do it using chain replication. We do it using chain replication. Please.
Are you, so is it that I'm forced to make one log because I'm making another log, so
Yeah.
L1 and L2 are there, and I want to use L1.
Absolutely.
Am I forced to
Yes. So this is a very nifty problem. And let me pose a queuing theory problem which I don't know an answer to. So the question is, think of this as think of these sequence of locks as a network. Okay. So what I'm doing is I'm showing up at the first station. I'm trying to get that lock, and now I'm showing up at the next station. I'm trying to get that lock, and so on. Okay. So you can build this entire network. Somebody else is going to some other lock and then coming and meeting me at the next lock, and so there are all of these queues that form at these things. What lock coalescing does is it reduces the depth of the queues, but it increases the lines at individual locks. Okay? So empirically, we actually observe that the delay is super linear in the depth and linear in the width of the queue. Okay? I have never been able to prove this. Okay? But I can show by numbers that, let's say we're all playing this game where we're trying to catch 5 nested locks. Play this simple game. You generate 5 random nested locks. Of course, random is a bad example, but draw it from a Zipfian, a rather sharp Zipfian. So everybody draws 5 locks from a rather sharp Zipfian and plays this game where you're going to acquire the first lock, go to the next queue, acquire the next lock, and go to the next queue. It turns out that the delay that you see is not linear in this depth. It's not linear in the number of locks you're getting. It's actually significantly super linear in the depth, but it's linear in the width. And what lock coalescing is doing is it's reducing the depth of this nested locking that you're doing. And that's why you see this really significant improvement in performance. So if there are people who are really into queuing theory and who are good at queuing theory, this would be a very nice thing to be able to prove that for distributions like Zipfian, such nested locks are super linear in the depth, in the nesting depth of the locks.
Is the intuition that tasks often want to get groups of locks anyway?
Exactly.
Make them just buried at one shot.
Absolutely. So the way I describe this is, people coming from the US to Bangalore would likely go from JFK to Frankfurt and Frankfurt to Bangalore, or Detroit to Paris and Paris to Bangalore. So there's benefit in taking these locks and coalescing them into one lock. Yes, there will be some guy who only wants to fly from JFK to Frankfurt but not to Bangalore. But most of the people will take the entire route, and therefore you will gain. And the loss that you take is amortized and then some by the gain that you get. So the intuition is exactly that there are higher order relationships in these log groups that people have. All right. So I'm going to skip some of these things. We show really neat results where you can see that such log coalescing actually works very well. The open questions here, we do not show that this is the best way of doing it. We do not show that by any analytical means what the bounds on these things are, why they work. We mostly show empirically that one technique that we implemented works very well. Now, I've made this sound very simple. This is actually very complicated because when you're running these lock servers, even the operation of moving a lock state from one server to another state must itself be done transactionally. So to execute a transaction, you're now at the back end of a transaction trying to do all of these things transactionally. So these are very, very sophisticated pieces of software to actually write. Anyway, I'll skip these things, but I'll leave you with a few conclusions. So the weighting version of the SS2PL is a strong two-stage locking with increasing contention order, and partitioning outperforms other protocols very significantly. Now this is important. This is almost the key overhead of most distributed programs, and by doing essentially nothing, I've given you something that makes these things about 300% faster, and that only increases with the amount of contention. Restarts due to conflict constitute a major overhead in distributed transactions. Reducing restarts by busy waiting for locks an important step towards increasing performance. Understanding workload, even simple statistical contention is enough to achieve significant performance, 200-300%. Lock partitioning through graph clustering can be performed dynamically to achieve performance gains. These are all various takeaways that you can take from where we started quite a while back. So I'll stop at this point and I'll take any more questions that you might have. This is actually fun. All of this is open source software. You can download HDFS, you can download HBase, you can download Hadoop. You can start to do all of these things yourselves. It's very easy for you to set up a Hadoop cluster, use a small set of machines as your own lock servers. So these experiments you can run very easily yourselves. No more questions? Thank you, guys.
Thank you, sir. And, I request you to please accept this memento.
Thank you very much.